tile missing and a suspicious rope coming down from my ceiling. So I'm just going to climb this. If you would just give me a second here. Can't get into. Oh, I am in the ductwork. Interesting. Well, I'll just wander around here and see if I can find anything useful. What's this? Okay, sort of dark. And oh, look, a giant parking lot filled with buses. This must be chemistry. And in fact, it is. That's right. It's chemistry. Pay attention now. So we've talked before about the off-ball principle, and if not, you should go watch that video or talk to somebody about the off-ball principle, because this is going to be kind of quick here. It is the way electrons fit into orbitals with the 1s, 2s, 2p, all this nice diagram, starting from the top, and we go down, top left, down to the bottom right. And so the first one being 1s, and then next one is 2s, and then up top to the third diagonal goes 2p, and then 3s, and then 3p, and then 4s, and then back to 3d, 4p, and 5s, etc. And what I've done real quick is just lined all these buses out. I often talk about orbitals as buses. So these are just lined off with 5s and 4d. They're all labeled because each of these buses has its own custom parking spot, something that it stays there for the entire time. And when we have different types of buses that we can get on. So the S bus, for example, it's the first one. Look how tiny and nice it is. The S bus has a max rider of 2 people, just like the S orbital can only hold 2 electrons. And it seems to be getting dark. The P bus, let's go find one of those, has a max holding or max allowable rider spot of 6. It can only hold 6 electrons. The D bus, let's go find one of those before it gets too dark. The D bus can hold 10 electrons. So you got 2, 4, 6, 8, 10. And you might remember the Pauli exclusion principle says that you can't have 2 electrons facing the same way. If you're writing up in the box method, you can't have 2 up arrows or 2 down arrows. For me, that's like you have a bench and you have 2 seats, right? You have the aisle seat and you have the window seat. And you can't have 2 people sitting in this seat. One sits here and one sits here. And that's just the way it is. And it's dark. Let me take a nap, guys. I'm sorry. This is just... I'm quite refreshed now. And the last bus we'll talk about is the F bus. It's the biggest. There's one all the way back here. It takes a while to get to them. These hold 14 electrons, or 14 students if we're going to go with the bus metaphor. And there are 7 benches, and each bench, again, holds 2. One sits in the window seat, and one sits in the aisle seat. And you can never have 2 people in the window seat, and you can never have 2 people in the aisle seat. And it's also time to refresh ourselves about the empty bus seat rule, or the Huns rule, which says that when a student gets on the bus, they usually don't go through the top of the bus, they come on like this. They sit in an aisle seat, or they sit in a seat and they're happy, and then number 2 comes on the bus. He does not sit next to this guy, because it's taken. He sits over here. He wants his own bus. And so it says electrons will fill empty benches before they sit next to somebody else. So if I had 3 students on this bus, there would be 1 here, 1 here, and 1 here. The 4th one getting on would then fill the extra seat in the other one. The 5th one would then fill one of the other ones, and then the 6th one would fill the last seat, and the 7th one would not get on this bus because this bus is full and it is going places. So let's do a quick example here. Let's talk about sodium. So my example here is sodium. This is a pull from the periodic table. Has an atomic number of 11. The symbol is Na. It's Batman's favorite element. And then of course you have the name and the atomic mass. Now what I really care about is the number 11, because since my example just says sodium, it's not sodium minus or sodium plus 2 or sodium minus 3. That means there's no charge. And so if I have 11 as my atomic number, it means that I have 11 protons in the nucleus of sodium. And if I have 11 protons, that's like saying 11 positive magnets, then I'm going to have 11 electrons, because those are going to be opposite attract. So for it to be neutral, those numbers need to be even. So this means I have 11 electrons. And so for this bus, means I have 11 students, oh boy, to get on all of these buses. And I'm just going to start with bus 1S because it's the first one in line. I'm going to fill this bus up, I'm going to move to the next one, and fill this one up, and I'm going to keep going until I have all 11 electrons in their orbitals, or all 11 students on the buses. So let's start off here. So first I'm going to start off with the 1S bus. Excuse me. Now it's pretty simple. I've got two guys, one's going to go there, and one's going to go there. Pop. Window seat, aisle seat, this bus is full. Awesome. Moving on to the next one. Now the rest of these buses I've sort of cut off. Now, a side note, if you were drawing this, as you often will for diagrams, instead of writing window and aisle seat, that doesn't make much sense, we'd simply draw an up arrow and a down arrow. That represents the different spins. It's called spin up and spin down. But the point is that there's two spaces you can sit. So this is the down seat, this is the up seat, or whatever you'd say. Alright, so I've got 2 electrons in there. Now it's time to get another 2. So one there, one there. This bus is full. Moving on. Alright, here we are at the 2p bus. Let's follow Hund's rule real quick. So there's going to be an electron here, and then empty bus seat rule means he goes, next guy goes here, next guy goes here, fourth guy comes on the bus, he gets bus soup. Well, pretend he's in the right spot. And one there, and one there. Darn you. And so now there are 6 guys in this bus. Let's see if I can punch him back down into seat. Sit down, sit down. Nah, close enough. Alright, so that gives me a total of 10 if you've been following along with us. 10 people on the buses. So that means my last person on this bus will go to the 3S bus. He will come in here and he will sit all by him is lonesome because there's nobody else here. And so that I said he would sit there. That's right, he heard me. Anyway, let's write down that electron configuration real quick. So in order to do the electron configuration, all I do is just go back and list the number of buses, list the names of the buses and then the number of students on those buses, or the orbitals and the number of electrons. So the first bus in my list is the 1S bus. That says 12. The 1S bus, that is what I want to write. And then how many students fit on the S buses? Well, they only hold 2, so I'm going to put a little 2. Now normally this will be written kind of like an exponent. I'm just going to write 2 because I don't really have space here. So 1S2, dang it, I'm not good with S's and 2's today. 1S2. That held 2 of my students. So now let's go to the next bus. It's called the 2S bus, and it also held 2 students. Look at that. And now the next bus was called the 2P bus, and it held 6 students. And then the final bus, I just put one in, was called the 3S bus, and it held 1 student. Now quick check, if I take 2 plus 2 plus 6 plus 1 and add these all up, I should always get the number of electrons, which should equal the number of protons in this case because it's a neutral atom. And so I want to go back and look at this one, say 2 plus 2, that's 4, 4 plus 6 is 10, 10 plus 1 is 11, so I am okay, and everything works out well there. So another way to look at this would be something kind of like this. This is the electron configuration written out in a way that makes more sense, so you can actually see the exponents. And so using the off-ball principle, you just start here, because there's not always going to be Minecraft and buses to put students on. We start from the top right again, move down to the bottom left, and we just keep going through the whole process until we reach the end bus. And so there's my sodium, again, 1s2, 2s2, 2p6, 3s1. This is, right here, is the electron configuration of sodium. How you might draw this out on a box style, something you might see in class or on tests or something like that, might look something kind of like this, where I have just these blanks and the arrows may not be there. And so to draw the arrows in, we follow, again, the Pauli exclusion principle, which says I can't have 2 up arrows or 2 down arrows in the same spot, 1 up and 1 down only. And so I have 1 up, 1 down, 1 up, 1 down, and then Hund's rule says I'm going to have 3 ups in a row, up, 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 because they want their own space first, and then comes the down, 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 filling those up, and then lastly, the 3s fills that up there. And so that is the end of this little video. I hope this example has helped. And anyway, so have a good day and a good chemistry life, etc., and enjoy your time.